All right, let's talk about one of the most powerful and, let's be real, most hyped technologies out there, deep learning. We're going to peel back the layers and break down how an artificial mind actually learns to see and make sense of the world. Let's get right into it.
So let's start with a puzzle. How is it that an AI can write a surprisingly beautiful poem, but at the same time completely struggle with something that seems way more straightforward, like reading an MRI scan? The answer to that question gets to the very heart of why deep learning even exists. It all comes down to a fundamental problem of representation.
So what is this representation problem? Well, it's really just about how a computer sees the information we feed it. For any AI to do its job, the data has to be presented in a way it can actually understand. If that representation is wrong, the AI is basically blind before it even starts.
This slide shows you the challenge perfectly. See, early AI needed its data served up on a silver platter. On the left, you've got a doctor's report. It's got these neat, clean, structured features, like uterine scar, yes or no. A simple algorithm can gobble that up, no problem. But then look at the right. That's a raw MRI scan. It's just a chaotic grid of millions of pixels. To a simple AI, that's just noise. A single pixel means absolutely nothing on its own, and that is unstructured data, which is where early AI just hit a brick wall.
And this quote right here, it nails the core mission. The real trick is teaching a machine to look at all that messy, raw data and figure out what actually matters. It has to disentangle the factors of variation. Stuff like the lighting, the exact angle of the scan, the patient's position, and separate all of that from the one thing we actually care about. Is there a tumor or not? So how do you even begin to teach a machine to do that?
To answer that, we actually have to rewind the clock. We've got to go back to the very beginning, to the first real attempts to build a computer model of a brain cell, the very first artificial neurons.
And here it is. Meet the perceptron. Back in the 1950s, this was a mind-blowing idea, a simple little computational unit that could actually learn. It would take in those nice clean features we talked about and learn to give each one an importance, what we call a weight, before adding it all up to make a decision. It was a fantastic first step, but, and this is a big but, it still needed the data pre-trued for it. It was basically a very clever calculator, not a true vision system.
Which brings us to the big, multi-billion-dollar question. If a single one of these artificial neurons is just a fancy calculator, how do we get from that to an AI that can actually read a complex MRI scan? Well, the answer wasn't to build a better neuron. It was to start connecting them in a totally new way.
And that brings us to the power of layers. This is the simple, yet incredibly profound idea that gives deep learning its name. The breakthrough wasn't using one neuron, or even a handful of them. It was stacking them, creating a kind of hierarchy of understanding.
Here's how it works. The very first layer in the network looks directly at the raw pixels from that messy MRI scan. And each neuron in this layer has a really simple job. Find a tiny, basic pattern. It might be looking for a vertical edge, a horizontal line, or a slight curve. That's it. Think of it as the most basic, fundamental level of sight. Okay, now here's where it gets really clever. The second layer, it doesn't see the pixels at all. It only sees the output from that first layer, basically a map of where all the edges and corners are. Its job is to start combining those simple patterns into more complex shapes. It learns that, hey, a certain combination of edges makes a circle, or these specific lines and curves seem to form the outline of an organ.
And you can probably see where this is going. The process just keeps going, layer by layer. Deeper layers take those shapes and assemble them into even more abstract and meaningful concepts. So by the time you get to the very end of the network, it isn't seeing pixels or edges anymore. It has literally built its own internal representation of reality, a rich, complex understanding of what tumor looks like versus healthy tissue. It's solved the representation problem all by itself.
But wait, that just raises another huge question, right? How does the network know which weights to learn? How does it figure out that this particular combination of edges is super important, but that one is just noise? This is where the process of learning itself comes in.
The learning process is actually this really elegant and powerful feedback loop. First, the network just makes a guess. I think that's a tumor. Then, step 2, it checks how wrong it was by comparing its guess to the correct answer. The difference between the two is the error. Then, and this is the magic part, it uses some clever math to figure out exactly how to adjust each one of its millions of weights just a tiny bit to make that error a little smaller next time. And then it just repeats this loop. Guess, check, adjust, millions and millions of times, getting just a little bit smarter with every single cycle, until its predictions become unbelievably accurate.
Of course, it's not always that easy. One of the biggest hurdles is a classic problem called overfitting. This is what happens when the model gets so good at the data it's been training on that it basically just memorizes the answers. So its training error might be near zero, but the second you show it a brand new MRI scan it's never seen before, it completely falls apart. The goal isn't memorization, it's generalization. It needs to learn the underlying patterns, not just the answers to the test.
Okay, so if these core ideas have actually been around for decades, why are we only seeing this massive explosion in AI capabilities right now? Why is deep learning suddenly taking over the world?
Well, it's because of a perfect storm, a convergence of three huge factors that all finally came together. First, big data. These models are incredibly hungry for information, and for the first time, the internet gave us the gigantic data sets needed to feed them. Second, powerful hardware. Turns out the GPUs originally built for video games were perfect for the kind of math deep learning needs. And third, the algorithms themselves just got a whole lot smarter, thanks to decades of quiet, steady research finally paying off in a huge way.
And this gives you a sense of the mind-boggling scale we're talking about now. A single neuron in one of today's networks can have thousands of connections. We're now building models that are reaching the complexity of a mouse's brain. Some are even getting close to a cat's brain. It's this incredible scale, all powered by that trifecta of data, hardware, and algorithms, that's driving the modern AI revolution.
So we'll leave you with this. This whole hierarchical, layer-by-layer approach to learning has proven to be way more powerful than anyone could have imagined. It lets machines build their own understanding of the world from the ground up, finding patterns that we humans may never have even thought to look for. Which of course poses a pretty fascinating final question. If this is how AI learns to see, what hidden structures and patterns in our own world is it just now beginning to uncover that we, with our own biological brains, have missed all this time?